Thanks for coming, everyone. As Jason mentioned, I'm Reza Zadeh, CEO of Matroid and adjunct professor at Stanford. Today, I'd like to walk you through some of the challenges that we often face when taking research from university papers and labs and moving them into industry and building real products around them, so that hopefully you have some basis for what to expect when you're taking these papers and taking them into the real world. So 3 challenges I'm going to cover is how do we make sure that we can achieve adequate accuracy in the time that it takes to develop the product. Secondly, can we actually take the machine learning models and algorithms that are available and scale them to the number of users that the product is going to be serving? And lastly, and most importantly, I want to focus on user interfaces. This is the part that gets the least amount of attention when a machine learning engineer tries to take their work into industry. So, adequate accuracy. What do I mean by this? If someone tells you, well, look, my model has 99% accuracy, that sounds really impressive at first glance. And in research and in university settings, that's often really amazing. And it's you think, well, it's time for me to now build a product around my research. Well, that's 99% accuracy is perfectly fine for if you have a who to follow suggestion on Twitter or an ad impression somewhere else. But it's completely unacceptable when you're going into a life and death situation like a self-driving car. If you put a 99% accurate object detector in a self-driving car, that means every 100th day you have you're going to probably die, which is completely unacceptable, right? So you have to be careful with this. And this is the kind of mistake that has made us not have self-driving cars yet, is looking out into the future and seeing what does it take to really get these things good enough to solve the task that they promise to solve. We have 99% accurate object detectors, but frankly, they don't work that well. They don't work well enough for self-driving cars. And this is part of the reason that self-driving cars have been 5 years away for the past 13 years. Ever since the DARPA Grand Challenge, we've been waiting for self-driving cars, and we're sort of, it's been 5 years away, 5 years away, 5 years away since then. It's been a similar story with machine translation. I started my career in 2007 working at Google Translate as an 18-year-old. And even back then, there was a 50-year history of machine translation research. And since then, there's been another 13 years, 12 years of machine translation research. And we're still not at a point where it's hugely solved or dramatically better than 10 years ago. It's a little bit better than 10 years ago with deep learning models. But if you were out thinking, well, suddenly my model is so much better than before, I can make a product out of this that no one's ever thought of, you really have to understand how much work has been done before you, how much work do you have to do to make this amazing. The example of a success story is speech recognition. Speech recognition over the past 5-6 years with deep learning has gone through a step function where it's suddenly gotten so good enough that many more new products and applications can be knocked off with it. So, for example, keyword searches with speech are now actually completely usable. It's not annoying to try and search with your phone, but it used to be annoying 5 years ago. It used to be annoying to text your friends with speech recognition. It is now completely usable, and that's changed in the past 5 years. So if you were making a company 5 years ago around this, you made the right bet. If you didn't, if you'd made it earlier, you'd made a wrong bet. So how do you know? You need to be able to look at the current research, look at your application, and understand the roadmap precisely for the next decade at least. Computer vision is actually what Matroid, my company, is focused on. And we believe, and we wholeheartedly see in the market now, that computer vision is now ready for products and ready for industry. Computer vision research has been around for decades as well. And really only in the past 4 years is it the case that you can now release computer vision products that are solving real-world problems that is and showing value as opposed to just being cool demos. So accuracy here was the bottleneck, and now the floodgates have opened. We have 99% accurate object detectors. I would not recommend putting them in a self-driving car because 99% accuracy is not good enough for a self-driving car. But if your application is media analysis, if your application is tracking all kinds of things that happen in TV, in surveillance cameras, and in other places where a 1% error is not the worst thing in the world, then you can see real value from those situations. So problems like this, where you have the president of China behind the desk, his chair, and his table have been accurately described. And if you're tracking the president of China across all media, this is a great way of doing it. There's no need to hire an intern and have them watch all the TV channels in the world 24/7. You should totally automate this now. And products like this are coming into the market. This is why we started Matroid. So only tasks that can tolerate error can be made into products. And you might think, well, OK, computer vision is solved now. Let's go make all the computer vision products. No. Right now, only detection of nouns is done well enough. So we can detect cars, we can detect pedestrians with 99% accuracy. But verbs are harder now. So detecting whether someone is picking up a phone versus making a call, these are subtle differences that come out when you're building detectors for verbs. And this is, I claim, not yet quite good enough for industry. We are working hard on the research behind this at Stanford and other places, but I would be careful in that if you're going to start a product in this area, you better have a really good understanding of where it's going in 5 years. And sometimes accuracy is actually totally unimportant. If your application is an artistic one and one where subjectivity is abound, then as long as what you want to do looks good to you, then you might actually be fine. So here we have a general adversarial network trained on and generating real human faces. These are all fake people. They've all been generated using a network, and they look almost real. So if you're a game developer and you want to generate faces that look in some way, it's great. If you're building an app for changing photos the way they look, just putting filters on photos that you already have. This, as long as it looks good to you, it's good enough to use. So there are places where the adequate accuracy is incredibly low because the bar is very subjective. So the key takeaway is that you really, really have to think about adequate accuracy out far in the next decade. And this sounds almost obvious, but it's been the reason for the failure of many machine learning products, and it's even brought entire AI winters and problems with funding in AI. So I really encourage you, before going out into industry, think about your next decade. The next thing I want to talk to you about is scaling machine learning. The typical machine learning pipeline looks like this. You all know this pipeline. Every single one of these text boxes, the data, algorithm, model, replicating models, and serving models, and repeating the whole pipeline, every single one of these text boxes can be scaled, and there are entire research communities dedicated to looking at every single one of these text boxes, and that is no exaggeration. I have a conference that looks at scaled machine learning, and there are entire mini communities behind each one of these. So for Matroid, we actually care about, in particular, large data and large models, and computer vision was made to achieve adequate accuracy using really old models, but scaling up the data and scaling up the number of models that could be trained at the same time. So sometimes scaling machine learning is your bottleneck to achieving adequate accuracy. And so you have to also keep in mind how much scaling can benefit you. So in that light, I want to tell you about this trend towards software 2.0, where what we're seeing is CPUs, GPUs are essentially taking over the entire computing stack, not just machine learning computations, but the parts of a CPU, GPU, and TPU that do machine learning computations are taking over all of software. They're doing that by first taking over linear algebra, which is taking over deep learning, which is taking over machine learning, which is taking over AI, which is taking over software, and software is eating the world. So what we're seeing is an abundance of chip manufacturers building